So far in our discussions of counting molecules in the mole, we've focused on pure substances, pure solids, liquids, or gases, where the substance is the same everywhere. So if we know something about a single molecule of that substance, we actually know something about the substance on the macroscopic level, since it's the same everywhere. It's a pure substance, only consists of one type of atom or molecule. In this video, we're going to broaden our horizons a little bit and think about counting molecules in mixtures, specifically in homogeneous mixtures, which we'll call solutions. And so we'll first of all take a look at the submicroscopic picture. We're going to deliver on a promise I made earlier to return to submicroscopic models and the submicroscopic picture for liquid solutions in particular. And we're going to learn to identify the components of a solution based on primarily their relative numbers, as we'll see. We'll talk about a key measure of solutions called concentration. Concentration, like molar mass and molar volume, is a bridge for us from a measurable quantity for a solution to the number of particles in that solution that we're interested in. So it's a bridge from, for example, volume to moles or volume to mass. Molarity, in particular, is a concentration unit that allows us to bridge volume and moles. And it's the most important concentration unit in chemistry by far. So we're going to end the video by talking about molarity, and we're going to apply it to calculate the amount of solute from the volume of a solution, or vice versa. Molarity is a key bridge in thinking about solutions from the measured world of solution volumes to the chemist brain world of counting molecules. Whether you know it or not, you deal with solutions on a daily basis, and you've probably had the experience of preparing a solution before, dissolving, say, salt and sugar in water and watching those solid granules of salt or sugar kind of dissipate and disperse and eventually disappear until you're left with a liquid that looks a lot like pure water, but that we know, based on conservation of mass, has to contain salt or sugar particles within the solution. Key to a solution is that it's a homogeneous mixture. This means that the solution is basically the same everywhere. Now, this can't possibly be true in practice, right? Since on the molecular level, we'll have water molecules in some places and sugar molecules in others, for example, in this sucrose solution that we're seeing on this slide. But on average, the average appearance of the solution is the same everywhere. It's not heterogeneous with different phases in different places. It's all one relatively uniform phase that we call a solution. A solution is by definition a mixture, and so will contain at least two components. One of those components will be present in greatest amount. We call this the solvent. In the solution you see on this slide, the solvent is water. Most of the molecules are H2O. The minor components within a solution, and there may be more than one, are called solutes. And we say that the solutes dissolve in the solvent. So when we take solid sucrose, for example, throw it in water, stir it around. As the solid sucrose disperses and disappears into the liquid, we say that the sucrose dissolves in the water. And there are many, many more water molecules in that solution than there are sucrose molecules. This is one reason the solution retains the appearance of a liquid. It looks mostly like water because it mostly is water, right? And this is very typical of liquid solutions, and in particular liquid solutions in which water is the solvent. Solutions with water solvent are the most important types of solutions that you'll see in your introductory chemistry course, and so we give them a special name. They're called aqueous solutions or aqueous solutions. And to think about solutes that are dissolved in an aqueous or aqueous solution, we use the phase designator AQ in chemical equations. This indicates that that substance is not present in pure form, but is bathed in or surrounded by water molecules. So for example, if we put some sucrose into an aqueous solution and then say treated that aqueous solution with something else to try to get the sucrose molecules to react, the way we would represent the sucrose in a chemical equation is with its chemical formula followed by the AQ phase designator. The mental image here is not solid sucrose, but something like this, sucrose dissolved in water. So each of those individual sucrose molecules is surrounded in or bathed in, you could even say, right, in the context of a liquid solution, water molecules. And this is important to keep in mind, and actually the AQ phase designator can be used a couple of different ways. I just mentioned that it's frequently used to refer to the solute when the solute is in an aqueous solution. So we can talk about C12H22O11, sucrose molecules, in the aqueous phase. But you'll also see this same representation, the same symbolic representation, used to refer to the macroscopic level, right? The solution as a whole. There's a bit of ambiguity here between the domains of chemistry, going back to Johnstone's triangle, right? This symbolic representation can be used for both the submicroscopic level of a single sucrose molecule dissolved in aqueous solution, or the macroscopic level of the solution as a whole, with mostly water molecules and a little bit of sucrose in there. Counting molecules in solution, counting solute molecules in solution, can be a little bit tricky because we no longer can rely on molar mass. When I weigh an aqueous solution of sucrose, a solution of sucrose in water, the weight is mostly H2O with a little bit of C12H22O11. And actually, the molar mass of that compound of sucrose doesn't help me at all in determining the number of sucrose molecules in this solution, since I don't know how much mass is water and how much mass is sucrose. In order to count sucrose molecules in this solution, we need a different measure, some measure that allows us to go from the mass or volume of the solution as a whole to the mass or volume or number of moles of sucrose particles in that solution. And the conceptual measure here, the big idea, is what we call concentration. Probably a term you've heard before. Certainly if you've looked at a bottle of orange juice, right, you may have seen "from concentrate" on the label, and concentrate refers to a solution with a large number of solute particles per fixed volume or mass of the solution. Concentration is the amount, mass, or volume of a solute in a fixed amount, mass, or volume of solvent, or most commonly, solution. Conceptually, it's a measure of the solute density. The higher the concentration, the more solute particles we would see if we were to zoom in and look at the solution at a fixed volume on the submicroscopic level. And this image from Wikipedia really does the job well, showing what we mean by concentration. In the concentrated solution on the left, the first thing to notice on the macroscopic level is that it's a deeper color, and this is because the solute is colored, the solute is red. And if we zoom in to the submicroscopic level, we see quite a few red triangles. The solute molecules here are red triangles. And these red triangles are giving rise to this deep red color. When we add liquid to this solution to increase the volume while keeping the number of solute particles fixed, we've done what's called dilution. And so the solution on the right is more dilute than the solution on the left. Dilute is the opposite of concentrated, essentially, here. And what we see on the submicroscopic level here is that the density of solute particles is much lower, right? If we zoom in on that same volume, we see only 1, 2, 3, 4, 5 solute particles on the right, where we saw in that same volume looks like more than twice as many solute particles in the concentrated solution on the left. And so conceptually here, higher concentration is associated with the greater density of solute species in the solution. And we can already begin to start thinking about the appropriate units here. Maybe it's the mass of those red triangles per liter of solution. Maybe it's the number of moles of those red triangles per liter of solution, something along these lines. These are both units of concentration. This slide summarizes some of the most common measures of concentration. Actually, the most common and most important is on the next slide. The thing you'll notice about all of them, and I've tried to color code to make this clear, is that they're all related to, they're all proportionalities, first of all. We'll come to that in a second. Proportionalities between an amount or mass or volume of solute and an amount or mass or volume of the solution as a whole. So for example, percent by mass is the mass of solute per 100 grams of the solution, or the mass of the solute per unit mass of the solution times 100%. Percent by volume, a similar idea. We take the volume that the solute would occupy, divide that by the unit volume of the solution, multiply by 100%. You'll sometimes confusingly see mass and volume, or weight, the W in this representation refers to weight here. You'll see weight and volume mixed, so mass volume percentage, where it's the mass of the solute per unit volume of the solution times 100%. You'll see this sometimes expressed, for example, without the percentage as grams per milliliter. This comes up with parts per million as well in some cases. And then there's mole fraction, which is actually a very sort of fundamental concentration unit that simply involves counting solute and solvent particles and saying, okay, say I've got, and I'm just ballparking here, 100 particles in, let's do the dilute solution, 100 particles in here, and 5 of those are solute particles. The mole fraction of solute is 0.05 or 5%, right? Since 5% of the particles in the solution are solute particles. This is what we mean by mole fraction, the number of solute particles divided by the total number of particles in the solution. Now, each of these, as I mentioned earlier, reflects a proportionality between the amount of solute and amount of solution. And I want to show this with a graph to drive this point home about proportionality. Obviously, if we have zero solution, if the amount of solution is 0, there's nothing there, the amount of solute is 0. As we increase, say, the mass of the solution, 1 gram, 2 grams, 3 grams, 4 grams, 5 grams, etc., the amount of solute in that growing solution increases linearly, right? If I add a gram, I get some additional amount of solute. I add another gram, I get that same additional amount of solute. And so the amount of solute varies linearly with the amount of solution. And the slope of this line, the ratio of the amount of solute to the amount of solution, exactly is concentration. So concentration reflects this proportionality between the amount of solution, and this we can very commonly measure, right? Using a balance to get the mass, or a pipette to get the volume, or what have you, burette to get the volume. And so we can go from measured mass or volume to the amount of solute, something we cannot see, right? This might be a number of moles of solute particles or a mass of solute particles inside a solution that we've measured, something like this. So this proportionality idea is key, and you'll notice all of these units include the division symbol. They're all proportionalities between the solute and the solution. Let's do a little practice now with units of concentration by addressing the example problems on this slide. Concentrated hydrochloric acid, nasty stuff, has a concentration of 37.2% by mass. The question here is, if I've got a sample of concentrated hydrochloric acid weighing 85 grams, what mass of HCl, the solute, is present in this solution? The first point I want to make about this is this solution is mostly water. This phase designator tells me the solution is mostly water. It's by mass, something like 62.8% water and 37.2% HCl molecules. That 37.2% is a kind of proportionality, right? What this tells us is in 100 grams of this solution, there are 37.2 grams of HCl. So if I want to answer the question, how many grams of HCl are there in 85 grams of the solution, which I'm going to abbreviate here as SOL' for solution, I can use this proportionality, and you can probably already see where this is going by multiplying by this proportionality between the mass of HCl and the mass of solution. We'll get a cancellation of the gram solution units, and we'll get the mass of HCl remaining, and this turns out to be 31.7 grams of HCl. And so notice we scaled down the solution volume from 100 to 85. That's about 5/6. Then sure enough, the mass of HCl is about 5/6 in that scaled down solution. Now the next question is interesting because it's a little bit confusing in the way it's phrased in the units we use. The density, the mass density of concentrated hydrochloric acid is 1.19 grams per milliliter. This means for the solution as a whole, if I back up to our macroscopic picture of a solution, for this solution as a whole, the density is 1.19 grams per milliliter. If I'm looking at a milliliter here, the mass of it is 1.19 grams. Okay, Knowing that and knowing what we do about the concentration of concentrated hydrochloric acid, this 37.2% by mass, the question is, what is the concentration of concentrated HCl in units of grams per milliliter? So this grams per milliliter is grams per milliliter of solution. Grams of HCl per milliliter of solution, not grams of solution per milliliter of solution, which is the density. So those units are different, and the difference is actually in the grams. Grams of solution here, solution per solution for the density, grams of solute here for the concentration. All right, so how do we begin thinking about this? Well, let's start again with this proportionality between the grams of HCl and the grams of solution. In essence, we want to convert this percent by mass concentration into a concentration in units of grams per milliliter. And we can do that by thinking carefully about the density. So I'm going to switch up colors here so we can think about the density, 1.19 grams per milliliter. Where we want to go here, right, for our final result is something that has grams of HCl in the numerator, and then in the denominator, we want milliliters of solution, right? And so we need the grams of solution per milliliter of solution, or the density, in order to do this. And to get the units right, we need to multiply by the density. So 1.19 grams of solution for every milliliter of solution. In terms of proportional reasoning, essentially what we're saying here is, okay, if I have 100 grams of solution, I know the volume of that by dividing by the density, essentially, right? And that's in essence what we're doing here. Dividing by the density in the denominator of this proportionality is the same as multiplying by the density. And so I'm finding the volume of the solution down here in the denominator, and I already know the mass of the solute based on the mass percent concentration that was given here. And so when all is said and done here, we end up with 0.443 grams of HCl, and actually the units are already there, right? Grams of HCl per milliliter of solution, and I like being very explicit, especially when we're first starting out with concentration, about grams of what and milliliters of what. Here we're referring to concentration, the grams of the HCl solute per milliliter of HCl solution. By far the most important and most widely used concentration unit in chemistry is molarity. And molarity is the proportionality between the moles of a solute in a solution and the volume of the solution in liters specifically. So the units are moles of solute per liter of solution. Actually, reading that whole thing out a few times is good practice if you're just seeing molarity for the first time. We represent it with moles per liter, or just a capital M. And as I mentioned back when we first introduced moles, it's very common and very useful conceptually to include a chemical formula after moles per liter, or this capital M, to clarify exactly what we're talking about with moles. Moles of what, right? To answer that question of moles of what. And molarity, again, is this proportionality between the volume of a solution and the number of moles of solute within it. So what molarity allows us to do is use volume of a solution to count the number of solute particles in that solution. And this is valuable, right? It's valuable for the same reason that molar mass is valuable. We can use a laboratory measurement, in this case of volume, to count something we cannot see, the number of solute particles in the solution. Molarity is often denoted with this X in square brackets, where X is a chemical formula, and this is the chemical formula that answers that question, moles of what? And the mental image you want to have here is, imagine we had the solution in a volume that was 1 liter, and there were some solute particles in that solution. Here I've represented them as red dots, and there are some number of moles, X in square brackets, moles of the solute in there. The molarity would then be X in square brackets moles divided by 1 liter, or just X moles per liter, right? So this is kind of the picture in our minds of molarity. 1 liter of volume, how many moles of solute are present in that 1 liter of volume? Let's build on our previous work determining the mass volume concentration of concentrated HCl to determine the corresponding molarity. Molarity is defined as N, the number of moles of HCl solute, divided by V, the total volume of the solution. And what we can do here is assume 1 milliliter of solution to get the volume straight away and proceed from there, figuring out the number of moles of HCl that corresponds to this mass of HCl. To find that, we use the molar mass as we have previously, dividing the given mass by the molar mass to get 0.0122 moles of HCl in a milliliter of this solution in this case. The volume, as we just mentioned, is 1 milliliter, but to get the units right, we need to convert this to liters. And so I'm going to divide by 1,000 or multiply by 1 liter for every 1,000 milliliters to get the units into liters, 0.001. And then the corresponding molarity is just this number of moles of HCl divided by this volume of the solution, which comes out to 12.2 moles per liter. And in fact, you can go out on the internet and Google what is the molarity of concentrated HCl, and this is the number that you'll see. This is actually among the highest possible concentrations for HCl in water. And now I want to emphasize this idea of molarity as a proportionality between volume and number of moles. Say we had 375 milliliters of concentrated HCl. How many moles of HCl are present in this solution? Well, now we use the 12.2 moles per liter as a proportionality. We can write out, for example, that a volume of 1,000 milliliters of this solution contains 12.2 moles of HCl. This is a proportionality, and so we can set it up as such. 12.2 moles of HCl divided by 1,000 milliliters, right? There are 12.2 moles of HCl for every 1,000 milliliters of the solution. We've got, in this particular example, 375 milliliters of the solution. And multiplying all this out, we arrive at the moles of HCl, 4.58. Notice we've got about a third of a liter in terms of the volume, and the number of moles of HCl we have is about a third of the number of moles in a liter of concentrated HCl. Proportionality, right? Lower volume means a lower number of moles, and the relationship is linear. So we can do this kind of linear multiplication in order to figure this out. We haven't touched on all the units you'll come across of concentration. For example, parts per million and parts per billion are common in the water quality world, where we want to keep bad things out of the municipal water supply, keeping them at very, very low concentrations. And this is the great thing about ppm and ppb. That's all I'll say about these other concentration units for now. Another lingering question you might have is about ionic compounds, which separate into their component ions when they dissolve in water. When you take sodium chloride and dissolve it in water, the sodium cations and chloride anions drift apart, and each is independently surrounded by water molecules. How does dissociation affect the molarities of ions, especially in ionic compounds where I have more than one copy of an ion, something like CaCl2 or FeCl3? Are the molarities of these ions in solution equal to the molarity of the formula unit in solution? As you may have guessed, probably not. And in your introductory chemistry course, you'll learn about the mechanics of that and how that works and how to visualize the dissociation process. Then the third question here relates to properties that are connected to molarity. How do we measure a molarity in the first place, right? Given that we can't see particles in a solution. One way, of course, involves preparing the solution so that we know, for example, the mass of solute and the moles of solute that we put in to make a known volume of solution. But what if we're fishing an environmental sample of water from a lake or a river? How can we measure things to determine the molarities of various solutes in that environmental water sample is an open question, and one that, yet again, you'll explore in your introductory chemistry courses and beyond.